Alright, hi everyone, welcome to the video for Unit 2 Lesson 7, where we're going to be working with our proofs with segment addition and subtraction. So in this lesson, we're adding to our list of properties and to our theorems, and we already have some exposure to these concepts that we're going to be working with today from early on in our curriculum. Where if you guys remember, sometimes we were algebraically solving for missing pieces of segments. Sometimes it's also going to help us if we relate these ideas back to those numerical examples, it's going to help us understand the concepts a little bit more. Before we get into it though, just a refresher on some vocabulary. So this is a refresher on the definition of a midpoint. Now again, we know that a midpoint is in the middle of a segment, but we have to get in the habit of making conclusions that we can use in our proofs, right? So if we know something's the midpoint, the first thing that you should be thinking of from the definition is that a midpoint splits our segment into two congruent parts, right? Now from that, knowing that part of the definition, I would be able to conclude that this distance, let's call the midpoint M, we would be able to conclude that AM is congruent to MB. So just be on the lookout because we are going to be using that in our lesson at some point today. All right, so the first postulate we're going to go over is called the segment addition postulate. And again, with this one, we've seen it a little bit before, but we'll go over it anyway. So segment addition is just allowing you to break up a segment into the sum of its pieces. So let's say you have a proof diagram that looks something like this. What you might actually have to do, and you'll have to do this a lot, almost for every question in this lesson, where you're going to have to break that segment up into parts. So the segment addition postulate lets you take the smaller pieces and add them together to get the value of the whole thing. So in this case, and notice in your notes you have segment examples that you have to fill in and algebraic examples, so make sure you're filling in both of those equations. So in this case, we have AB, where if we take this piece here, if we take AB and we add it to BC, if we take those lengths and we add them together, we're just going to get the entire value of AC. Now that's just working with our segment notation, but to better understand it, we can apply some numbers to it as well. You guys can kind of already see them on the screen. However, if we know that AB is 4 centimeters, and then we add BC onto it, which is 10 centimeters, you'll see that if we add those two together, we'll get the value of our entire segment, which is 14 centimeters. So again, we're just taking our segments, breaking them into smaller pieces, and adding those pieces together. Now, one other thing we didn't really see much of is the addition axiom of equality. Now, these words of these axioms can be a little bit confusing. That's why it's so beneficial to look at these examples. So in this case, it says, if a segment is added to two congruent segments, then the sums are congruent. Bunch of word babble. So let's just get into our examples. So for our segment example, we're going to start with the fact that AB is congruent to CD. Now remember, congruent just means they have the same measure, right? So in our segment example, let's say I take AB and I add EF onto it. That's going to be the same exact thing. It's going to be equal to the fact, hey, if I take CD and I add EF onto it as well, they're going to have the same value. And the reason there is because EF is never going to change, right? EF is always just going to be whatever measure EF is. However, here we can see we have a difference. We have AB here and we have CD here. However, this given information tells me they're the same exact thing. They have the same value. So it doesn't matter whether I do AB plus EF or CD plus EF, they're going to equate to the same thing. Now, algebraically, you might help apply some numbers to it to help you understand. If AB was 5 and CD was 5, let's say EF was 3, again, over here, I said if we did AB plus EF, it's going to be the same thing as CD plus EF. Let's test that out. So if I do AB plus EF, it's going to be 5 plus 3. If I do CD plus EF, it's again going to be 5 plus 3. And if you do that addition, you'll see that they are actually equal to each other, right? And it doesn't matter whether this was, we chose 5 and 5 for A, B, and CD. It doesn't matter what number you choose. It doesn't matter what number you choose for EF, as long as you're following the fact that we have these two congruent segments, right? It says if a segment is added to two congruent segments, then the sums are congruent. So again, doesn't matter what numbers you choose. you will get the same thing. So make sure you have both of these equations written down in your notes so you can get full credit. Now, along with segment addition, we can also do what's called segment subtraction. Now, you can probably assume from the name, but what we're going to be doing is instead of taking the smaller pieces and adding them up to get the bigger one, what we're actually going to do is take the value of the entire segment here, right, which is AC. And what we are allowed to do is take segments away. Now, if we take segments away, we can just figure out what we'd be left with, right? So if I took AC and I subtracted the segment BC from it, if I did AC minus BC, what we can see visually is that we're going to be left with this piece here. We're going to be left with AB. Now, if you had to make this type of equation in your proof, how you would justify it is, hey, the segment subtraction postulate. I'm allowed to do this. I'm allowed to take segments away and figure out what I'm left with, right? Now, again, you could have done this also. You could have taken AC and subtracted AB from it, and in that case, you'd be left with BC, but we're just going to stick with this example for now. And it might help to also think about this numerically, right? So we have that the whole value of AC is 14. So if I take the whole entire value of 14, right? And then I take away 5. What I'm going to be left with is 9 units, right? And that may be beneficial. Like AB wasn't filled in for us as a value, but we just figured out that it was 9, right? So this might be helpful in cases where, again, you're trying to find the value of missing pieces or whatever the case may be. Just know that you are allowed to subtract pieces away from your segment if you need to. All right, now the subtraction axiom of equality says if a segment is subtracted from congruent segments, then the differences are congruent. So this is just like the addition property or axiom of equality. Now remember, we started with 2 congruent segments, so we're starting with 2 congruent segments again. And what I'm actually going to do here, I know in your notes you have this diagram, but I am going to go ahead and actually give you guys a different one. So let's use the same diagram that we had from before, where we had AB, we had CD, and then we had E and F. So this is going to be the same diagram as our segment addition. Now, what this says, again, let's say we're starting with AB being congruent to CD. So I know these two are congruent. Now, what the subtraction axiom of equality is saying, hey, if I take AB and I subtract EF, that's going to be the same thing. It's going to be the same exact value if I took CD and subtracted EF. Now, the same logic follows, right? EF is not changing. Right? EF is just EF, whatever number it may be. The only thing that is changing is this AB and this CD here. However, we know that they're congruent to each other, right? So those values aren't changing. Whether I write it as AB or CD, those values are still the same. So that says, again, in words, it's we subtracted a segment, we subtracted EF from 2 congruent segments, right? So those results have to be congruent to one another. Now, algebraically, we're going to use the same exact diagram. So we have A, B, C, D, and E, F. Now let's say A, B, and C, D, let's use 10 this time. So A, B, and C, D are congruent, they're 10, and let's use 5 for E, F. So again, we said if I took A, B, which is 10, and I subtracted E, F, which is 5, we said that's going to be equal to doing C, D, which is 10, minus EF, right? And if you did the math, you could see that it's going to work out that 5 is equal to 5, right? So again, it does help bringing this back to our algebra, just to kind of understand what's happening here. And again, if you had to use this in a proof, you would justify it by saying, hey, subtraction axiom of equality. All right, last couple things. So reflexive property is used to say that a segment is congruent to itself. So in your proof, as silly as it may seem, there might be times where you need to say something like, hey, your statement will be NP is congruent to NP, and your reason, so this would be your statement, your reason would be reflexive property, right? I remember this as saying like, hey, reflexive is almost like you're reflecting. So like, if I'm reflecting and I'm saying I'm congruent to myself, that's reflexive property, right? I kind of use that to help me remember. So if we're given that MN which is here. Let's say we're given MN is congruent to PQ. Now let's say, in blue I'll mark it, let's say we wanted to prove that MP is congruent to NQ. Now if you remember, from the addition axiom of equality, we would be able to do this, right? We have our two congruent segments, we have MN and we have PQ, and we're adding the same segment onto both of those, right? So just by the addition axiom of equality, we'd be able to prove that. However, what you guys need to know is that what we're trying to prove MP is congruent to NQ. So what you need to notice is, I'll highlight this, let's do it in green. You should notice that NP is a part of both of those segments. It's a shared segment. It's a shared portion, right? So whenever you have a shared portion, you have to mention that shared portion. So even if we were doing angles or triangles or whatever the case we're doing, if there is a shared portion, you need to use reflexive property in your proof and say that that shared portion, which in this case is NP, you have to say that it's congruent to itself. All right, now we have substitution. So again, we've seen this in algebra, but you can use this property to swap out segments or values that are congruent to each other in equations, and this is something you guys use all the time. So let's say numerically, we know that we have an equation, we have 2x plus 26 equals 14. Let's say we also knew that x is 7. You guys know, you say, hey, okay, how do I solve this? You would substitute the value of x back in, right? So it's the same concept. You would take this equation and you would rewrite it as 2, and then you would substitute in the value of x. So technically you're doing 2 and you're substituting that x in there, plus 26 equals 14, right? So in a proof, if you went from this step to this step, your reason would have to be just substitution. That's exactly what you did, right? You substituted the value in there. Now, we're used to seeing this algebraically, but seeing it in terms of segments might be a little bit different. So let's say we know that AB is congruent to EF. Now remember, congruent means we have the same value. And let's say we also have this equation. Now this equation could have come up just by being able to use segment addition, right? Like if we had a picture of our segment and it was broken up, we could have gotten something like this. Now let's say we had AB plus CD equals GH. Now we know that AB is congruent to EF, right? So what's standing out to me here, and I'll circle this in blue, what's standing out to me is that I have this AB here, right? But I know that AB is congruent to EF, so we can substitute that EF in, right? So this equation, I can take this AB and I can substitute it out over here, right? So instead of writing AB plus CD equals GH, I can write EF plus CD equals GH, right? And if we use this in a proof, like if we wanted to get from this equation here to this equation here, our reason would just be substitution, right? Because that's exactly what we did. We just substituted in EF for AB. Now, some examples you might see, a good question to ask yourself is, hey, where do I start? Do I need to use addition or do I need to use subtraction? Now, look at what you're given, right? If we're given that MP is congruent to ST, you always want to label those, right? MP is congruent to ST, and we want to prove that MS is congruent to PT. So a good rule of thumb I like to use is I compare my givens to what I'm trying to prove. So my given statement, right, we had MP is congruent to ST. Now, when I look at what I'm trying to prove, what I notice is that my proving segments, what I want to prove, they are bigger than my original segments I'm given, right? MS is clearly longer than MP is, right? So if that's the case, that's a dead giveaway to me that I need to use segment addition to break up my pieces. And I would break up first MS, and then I would break up PT, and then see where I go from there. Now another example, let's take a look at this, trying to identify whether we're using addition or subtraction. So here we're given that AC is congruent to BD, right? And we want to prove that AB is congruent to CD. So now what I'm noticing is that the segments I'm given are much larger than the ones that I want to prove. So if this is the case, we're going to actually use subtraction. Now, again, you got to figure out which segments you need to break up, right? So I'm trying to get something about AB, and I start with AC. So we're going to first have to break up AC. We're going to have to break up BD, and then see if we can, using the stuff we just learned, see if we can determine something about AB and CD. Okay, so you guys have these notes to refer to. Make sure you have everything filled in so that you can get full credit and so that you can have them to refer to as you work tomorrow.